Hello everyone and welcome back to this next lecture in the machines video series, and this is where we had left off last week, where we had drawn the flux diagram for a cylindrical rotor induction motor. So in this case I had represented both the stator and the rotor windings as the most simplified form of just two slots diametrically opposite each other and all the windings passing through these slots. So the rotor, even though it's a squirrel cage induction motor and consists of rotor bars along the circumference, we assume for simplicity that it consists of just these two bars or two coils with the same number of turns, producing a similar flux effect, right? So if we do consider that, and if we consider a single cylindrical rotor, we see that even if the rotor rotates, and we tried rotating it, we rotate in different directions, we find that there is absolutely no change in the reluctance of the flux path. For example, if you choose any of these flux lines, there is no change in the reluctance of the path of this flux if the rotor rotates. So therefore we concluded that the self-inductance of the stator is almost independent of the rotor. Right? Again, I say almost independent because there will be some non-regularities. For example, even if it's a squirrel cage induction rotor, there will be bars, and as it rotates, these bars will cause a change in the reluctance of the flux path. But this change is minute because we are talking about only a very small change in the reluctance. So you could say it's almost independent. So now the question then arises is, can we conclude this for any induction motor? And the answer to that is no. It depends on the construction of the rotor. In this particular case, since the rotor is cylindrical, we can say that if we assume the circumference to be smooth, then in that case, the reluctance of the flux path will not change, and therefore, or rather the reluctance of the flux produced by the stator current will not change, and therefore the stator inductance is constant. Now in this lecture, I'm going to show you another type of induction motor, which is a salient pole induction motor, where the rotor consists not of a cylinder, but of salient poles. Right? So as before I start this lecture, a brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can access on my own website, which is pythonpowerelectronics.com. So just click on this button, Learn, and this takes you to the list of courses which I have currently. So the very first course is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of using Python and Python Power Electronics to simulate power electronic circuits. The second course is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and Python packages such as the Signal package to analyze and design filters mainly for power engineering applications. The third course is called Simulation of Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components like inductors, coupled inductors, and transformers. The fourth course is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python control package to analyze and design controllers for power engineering applications with the specific case of a single phase inverter connected to a single phase grid. The last course is a free course which is called Why Specialize in Power Electronics, and this course is targeted towards either high school students or towards junior undergraduates to talk to them about some of the challenges and opportunities available in power electronics so that they can choose this as their domain of specialization. So all these courses are available on two platforms, which is Decibels Labs and Udemy, and if you click on these buttons, it will take you to that link. So the link for this course or this page is provided in the description of this video. If you're interested, please do check it out. So with this, let me get back to the diagram. So I have been trying to edit this and unfortunately I can't. So the only thing to do is I need to create a new one. So here I'm going to just redraw the main stator. So I'm going to draw a large circle. This is the outer circumference of the stator. So just to give you an idea of what I'm trying to do, let me show you here. I'm drawing the outer circumference of the stator, and this is a cross section of the entire motor. So basically the stator consists of these two concentric circles. So let me draw that. or rather the cross section consists of these two concentric circles. This is the stator. So now that we have the stator, as before, we can draw our two slots. That's two. So this is one slot and this is the slot below. So for our reference, we have chosen that the slots, though they are concentric, we are assuming that the winding in any stator or any machine for that matter is usually distributed all around the circumference, right? But we are assuming that all the windings are in two slots which is diametrically opposite each other. This is a simplified representation which is usually useful in designing or rather in mapping out the flux lines. Usually you would consider for most analysis a distributed winding, but to just figure out the basic concepts of flux windings or rather flux paths, this is good enough to consider two concentric slots. So we can assume that the current is flowing into this and flowing out of this, right? So therefore, by right hand thumb rule, we can draw some concentric flux lines. Actually, we can continue to draw. So these are just the flux windings. So now that we have this, let me just copy all this. Still getting used to this software. And let me paste it here. And I think I can flip it because it needs to be flipped here. And let me draw this away. And I think I don't need the inner one. Yeah, just take this out and delete it. And I just pick it up again. Okay, so in reality, flux lines will not cross each other, so this will not happen. But assume that this is a mistake, assume that they are actually passing over each other. I could maybe move this one just a little to be technically correct. Magnetic flux lines don't usually cross each other like this. Okay, now at least we are technically correct. They are not crossing each other. You can say they are just sort of gliding over each other. So, by applying right hand thumb rule, if we say that the current is flowing into the page in this slot, then these flux lines will be in the clockwise direction. And if the current is flowing out of the page in this slot, then by using right hand thumb rule, the flux lines will be in the counterclockwise direction. So now the question we had is, in the previous case, we had a cylindrical rotor. So you might ask what other kind of rotor there is? Well, there is what is called as a salient pole rotor. A salient pole rotor is, let me show a comparison. Here the cylindrical, it is a complete cylinder. In the case of a salient pole, we have we have poles only at discrete locations. So for the rest of it, there will be a huge air gap. Let me just show you how that works. So the way I would draw it is, first I will draw a rectangle. And once I have the rectangle, I think maybe it's better to just use a free hand. That's not a good one. So assume here so let me just draw a straight line. So assume that this is a salient pole, right? This should actually be a perfect semicircle, which it is not. But let's just assume that this is one. So I'm just going to copy this over. And let me flip it. And let me move it over here. Right? So such a rotor is called a salient pole rotor, because now instead of having a cylinder, we have only so many poles as we have designed. Now so far we are talking about a 2-pole machine. Later on we can talk about multiple pole machines such as 4-pole machines or 6-pole machines. But if we have a 2-pole machines, then we have 2 salient poles diametrically opposite each other. And as you can see, there is a huge air gap in the other parts. Now, if we were to look at the flux path and we were to look at the rotor position, you can clearly see that the flux will not have the same reluctance, or rather will not see the same reluctance depending on the rotor position. So for example, let me just quickly draw the axis. For some reason this became, now it is straight. So this is our axis, right? This is our horizontal axis, and as you can see, the axis of the rotor is also in the same direction. So let me just draw that as well. They are aligned to each other. So at this time you can see that the rotor angle is 0 because they are both aligned together, the horizontal axis and the rotor position. So let me just go over, pick out the rotor, and let me group this. So now this is a single machine, or rather a single object. Here, as you can see, the flux path of course is concentric. It's important to understand that this is not just the flux path. The flux path is flowing all throughout, right? Is flowing all throughout. So there are even a few more which I can draw actually. In this manner. So imagine a few flux paths like this. They are all flowing. So for example, this flux path typically will not flow completely out of this. It will flow through this midsection. So in this manner, you can consider, maybe I will just draw it by freehand because it's easier. This is a freehand. So if I draw this way, comes in and from here I can draw another one. And there are many such concentric lines. Now, what is important to understand is in this position of the rotor, when the rotor is horizontal and the axis of the rotor is totally 90 degrees or in quadrature with the axis formed by these stator poles, in that case the reluctance of the flux path is actually the least. The reason is that now the flux produced by these stator currents has a low air gap path for it to flow through. Now it's important to understand, as I said before, is the permeability of iron is much lesser than that of air, almost 1000 times lesser. So therefore, it is not the flux, or rather the reluctance faced anywhere in this magnetic medium is much lesser, almost 1000 times lesser than that in the air. So therefore, one need not assume that these are the only flux lines produced. It produces a vast number of flux lines, including many which will flow through this midsection. Now, in this midsection, the air gap has the least, it is the smallest air gap possible. Here, the air gap is maximum. So therefore, in this case, the reluctance faced by the air, reluctance of the air, or rather the total reluctance faced by the flux, is minimum in this midsection. Now, let me compare it to what happens if we rotate the rotor. So for example, I'm going to go over here. Actually, this is a quick path. Let me rotate it by 90 degrees. So in this position. Now, in this position, we have now rotated to 90 degrees. The axis of the rotor is aligned to the stator. For that matter, I can just rotate this as well. This is the axis of the rotor. Now, this axis of the rotor, you just bring it here so that they are aligned. This axis of the rotor is now in quadrature to the axis, to the horizontal axis that we had drawn before. Now the rotor position is theta is equal to 90 degrees or pi by 2, however you wish to say it. In this case now, the flux lines are totally different, right? The reason is because now the air gap is huge in this center. The air gap is the least only in this. So therefore the problem is it cannot flow. It is only a few flux paths which can actually flow through this pole. In the previous section, the flux paths were able to flow through the entire cross section. This entire midsection rather. Whereas now it cannot flow through the midsection, it can only flow through these salient poles themselves, that is these few flux lines. So therefore, it is quite obvious to see, whereas these flux lines outside now face a huge air gap, and therefore the reluctance is huge. As a result, the flux is very weak. So in this position, when the rotor is 90 degrees away from the horizontal axis and is aligned with these stator slots, it is very easy to see that the flux is much lesser. So in comparison, one can say that if I rotate this rotor, in this position the flux is maximum. Why? Because the flux can flow through the midsection and it can flow through this entire salient pole. Whereas in this position, the flux can only flow through a small part of the salient pole itself. So in this case, the reluctance is maximum and the flux is minimum. So therefore, in this case of a salient pole induction rotor, it is quite easy to see that the rotor position does have an impact on the flux. And if the rotor position has an impact on the flux, then in that case, the stator inductance is a function of the rotor angle. So therefore, in order to determine whether the stator inductance is impacted by the rotor angle, one must see what is the construction of the rotor. In the case of a cylindrical rotor, we saw that there is no impact at all. Wherever the rotor goes, the reluctance of the flux path remains the same. However, in the case of a salient pole induction rotor, it is quite obvious that there is a difference in the reluctance to the flux path, and therefore, quite obviously, the inductance will change. Now, I will not simulate an salient pole induction rotor, or rather salient pole rotor, anytime soon, because it's a fairly complicated case. But this is just for a glimpse onto how we go back to asking this fundamental question as to how these parameters are impacted by the rotor angle. So if you want to know whether a parameter is impacted by a rotor angle, you must draw such flux lines and try to figure out if, as the rotor rotates, is there a difference in the reluctance faced by the flux produced by the stator, or for that matter the rotor also. Whichever entity produces a flux, we must examine what is the reluctance faced by that flux path and if that reluctance changes with the movement of the rotor. This is a question which needs to be asked, and this is how we answer this question. So, with this, I'm going to end this lecture. This is just a kind of looking at this problem from another angle. That is, we saw in one case that there is no difference in the reluctance of the flux path to the rotor position, and in this case we are seeing that there is a difference in the reluctance of the flux path with respect to the rotor position. So with this, we will get back now in the next lecture to start examining what will happen to the rotor inductance and also the mutual inductance. So with this, I will end this lecture again. If you have any doubts, please do either send me a message or email me or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with the remaining parameters. Thank you so much and see you soon. Goodbye for now.